girls, this is lesson 6.3, and so this is a little bit different than the last two lessons that we looked at, but it's still about rational functions. So we're looking at operations and functions and compositions of functions. So compositions might be a new concept for you, so we're going to go over the properties of that in this lesson. So we have a couple of key terms. A power function, so that's a function that's written in the form y equals ax to the b power. And then a restriction we have with that is that a is a real number, and b is a rational number. And then our second definition is composition, and we'll address this a little later in this lesson. But a composition of a function g with f, we read it as g composed with f. And we write it function g, function f of x. And we're going to say that h of x is that function. So what this means is that we are going to do function f of x first. And then we're going to take that result and we're going to apply that to function g. So we'll explain this a little bit more in detail when we go through some examples, but that's the basic outline of composition functions. So first, let's look at some operations of functions. So we're looking at f and g. They're any two functions. So here's the example we're going to use. So this is going to be function f, and this is going to be function g. So we're going to define the composition, or we're going to define h of x based on operations of functions. So h of x says that h of x equals f of x plus g of x. So f of x is 3x. And we're going to add g of x, which is x plus 3. So here, addition is commutative. So we're going to look at 3x plus x. And the result of that, the sum of 3x plus x is 4x. And then lastly, we don't have anything. We're not adding anything. So that's like 3x plus 0. And in the second one, we're adding 3. So again, addition is commutative. So it doesn't matter which order we go in, but we're going to add all of those terms together. And so h of x equals 4x plus 3. Subtraction is going to work the same way. We're taking f of x, which is 3x, and we're subtracting g of x, which is x plus 3. So that's 3x minus x plus 3. 3x minus x is 2x. And actually, we're subtracting that whole function. So we have to distribute that negative side. So 3x minus x minus 3 is 2x minus 3. We can also do multiplication as an operation. So that's f of x times g of x. So again, f of x is 3x. And now we're going to multiply x plus 3. When we multiply 3x times x, we get 3x squared. 3x plus 3 is 9x. And then lastly, we can use the operation division. where we have f of x divided by g of x. So f of x is 3x, and we're dividing that by g of x, which is x plus 3. And we can't simplify that, so that's as far as we can go. This would be our final answer for h of x using the operation of division. So now let's think about, remember earlier this year when we defined domain and range? The domain, those are your possible x values. So what are our possible x values for this function h of x? What could x potentially be, and what could x potentially not be in order for this function to be defined as a function? So we're looking for x values that are in the domains of both f and g. So they have to be in both domains of the two functions that are involved in the operation. And the domain of the quotient does not include x values for which g of x equals 0. So here, g of x cannot equal 0. Because if g of x equals 0, then this function, h of x, is undefined, and therefore not a function. In any of the other operations, g of x could be 0 because you can always add 0, you can subtract 0, you can multiply by 0, and all of those functions are still defined. But if you're dividing, you cannot divide by 0. So in this case right here, we would say x plus 3 cannot equal 0. That means that x cannot equal negative 3. Because if x was negative 3, then we would have 3x divided by 0, which is undefined. So that's what this part means. G of x cannot be 0 because you cannot divide by 0. All right, let's look at a couple examples here. We're going to add and subtract functions. F of x plus g of x. So f of x is 3x to the 1/2. And g of x is negative 5x to the 1/2. Now, here we have to think of our properties of exponents. So we're looking at x to the 1/2 and x to the 1/2. So those are like terms, so we can take the difference of those two. 3 minus 5 is negative 2x to the 1/2, which is equal to negative 2 times the square root of x. The second one is f of x minus g of x. So that's 3x to the 1/2 power minus g of x, which is negative 5x to the 1/2. So here we have 3x to the 1/2, negative 5x to the 1/2, still like terms, like radicals. So we can combine those two terms, but now we're taking 3 minus a negative 5, which is the same as 3 plus 5. So that's 8x to the 1/2 power, which is 8 times the square root of x. Then our next step is to define the domains of f and g. So in f and g, x needs to be a non-negative number because you cannot take the square root of a negative number and get a real number. And here, same thing, can't take the square root of a negative number x needs to be a non-negative number. So therefore, in h of x, we need to pull from domains that are in f of x and g of x. So therefore, h of x has a domain of non-negative numbers. We can have 0, because we can take the square root of 0, that's 0, that number is defined. But we can't take the square root of a negative number. In this next example, we're multiplying and dividing, so this is where we have to be cautious here. G of x, we cannot divide by 0. Okay, but let's do the multiplication first. So f of x is 7x, and we're multiplying by g of x, which is x to the 1/6. So here, if we rewrite this, that's 7 times x to the first power times x to the 1/6 power. Your rules of rational exponents say that you add those two together. So that gives us 7 times x to the 7/6 power. Which, if you simplify this even further, that's 7x times the 6th root of x. Now in the second function, we're dividing. So f of x is still 7x, and we're dividing by x to the 1/6 power. Now we cannot divide, again, cannot divide by a negative, by the number 0, but we want to move this 1/6 power to the numerator. And to do that, we have 7 times x to the negative 1/6 power, which gives us 7x to the 5/6 power. Or 7 times the 6th root of x to the 5th. So now let's look at our domains of f times g and f divided by g. Again, g of x cannot equal 0. Therefore, x cannot equal 0. So in f of x, our domain here is all real numbers. X can really be anything. And our domain of g of x, it can't be 0, and we also can't take the 6th root of a negative number, because 6 is an even number, so we can't take an even root of a negative number. So therefore, we can only have positive real numbers. So since f of x has to be in the domain of f of x and g of x, h of x has to be in the domain of f of x and g of x, h of x is all positive real numbers.
I will post a second video that does the continuation of this lesson dealing with composition of functions, but please jot down any questions you have so far, and please bring them to class or next time I see you one-on-one. Thank you.